It's my pleasure to welcome Hussein Mozannar, whose work I've been following for a long time. Got his PhD at MIT last year, and is now a senior researcher at Microsoft doing work on human AI interaction and studying ways to augment people with AI tools to make them more productive. Can't wait to hear.
Thank you so much, Dan, and thank you everyone for coming here. I decided this morning to make a new talk. I scrapped all my slides, woke up at 6 a.m., made new slides, because I realized many of you had seen my previous talks. So this is work that we just wrapped up about a month ago at Microsoft Research AI Frontiers. The goal of this work is to build agents that can solve complex tasks. And I'll go into it a bit more. And so the system is called Magentic-One, and it's a really big team behind it, with main contributors Adam, Gagan, myself, Chang, and just a list of people who were essential to this project. So this is a big team contribution. So really the goal of this work is how can we design a system that can solve complex tasks that mainly require web-based and file-based navigation. So to be more concrete, I'm going to give you an example of some of the tasks this system is going to aim to solve. So the task is, of the cities in North America where country presidents were born, which two cities are the closest to each other? And so you can imagine to solve a task like this, you would need lots of different capabilities. Web search, not just superficial web search. You might have to dig deep into websites. You might have to write code to compute pairwise distances between cities. You have to run that code, and you'd have to keep track of where you are in the search over multiple steps. So this is not a very trivial task to solve that an LLM could solve if, even if it had this knowledge of the city coordinates. Another example, you want your system to order chicken shawarma, from the best place in Seattle and upload, the receipts to your expense reporting. And you would need web search, you would need file handling to upload things, and most importantly, you need good taste. So just a bunch of capabilities you would need your model to have. And just to be more concrete about what I mean about complex tasks is a task is going to be defined by an input, which is going to be a textual description and maybe some attachments. So you can have some files that you provide as input, a desired output that the task defines. So it's either a string answer or a new state of the world. Before I didn't have a shawarma, now I have a shawarma. And there is going to be an evaluation function. So given the desired output and any candidate output, you can give me a score between 0 or 1, whether I completed the task correctly or not. So these are big assumptions, but that's our scope is going to be today. So these measurable tasks. And the term complex is a bit hand-wavy, but we're really trying to think about tasks that require planning, acting, observing over multiple steps. So any task that can be completed in a single step is not something that's really in the scope of this work. And again, we're really focusing on the things that require web and file navigation, and to a small extent, coding. And again, please feel free to interrupt me at any time to answer any questions. And so what have people done in the literature to try to come up with such complex systems? And I'm going to try to categorize approaches as either single agent approaches or multi-agent approaches. So by single agent approach, what I really mean is you have an LLM and it's in a loop with itself. And the LLM can be augmented with tools and different prompting techniques. And one of the representative work of this kind is React. And so given a task, React will work like as follows. System will come up with a thought, an act, a tool call essentially, and then the result of that tool call, the observation. And then you just repeat that until the system determines it's completed. So it's an LLM in a loop, having access to these tools, and with this specific prompting techniques, that's thought, action, observation. And there's a bunch of, different ways to do prompting, different ways to do tool calls, different LLMs you can fine tune your model. But essentially, that's kind of the high level categorization I'm aiming for. And you could add fine tuning, you can add memory, you can add search. So all of these are things on top. The other category approach I'm going to have is you have multiple LLMs now working with each other. And the simplest realization of this is, reflection. And so I'm going to make a distinction between an LLM that acts and an LLM that verifies. And these could be the same underlying model, but it's a different prompt. So, and it could be different context that's fed into each of these models. So I'm going to make that separation clear. And so, the simplest example, you act, you reflect, you act, you reflect. There's like 3 search techniques that follow this similar methodology, but that's the general technique. You have action LLM and reflection LLM. The second technique is now, instead of just a single action LLM, you split it into multiple LLMs, each with different tools or prompts. And then you orchestrate them either in a deterministic workflow, where you can draw the graph out a priori, or in a dynamic workflow where the flow of execution is going to depend on the task instance itself. So I've just put up like paper from your group, Marg, and it's an instance of this multi-agent system with some form of workflow. And the approach we're going to take in this work is building a dynamic multi-agent system. So we're going to introduce Magentic-One, which is going to be based on a dynamic multi-agent architecture, which hopes to aim to solve these complex tasks. And to just walk through how Magentic-One will work before we go into the details. So here I have an example of these complex tasks from the Gaia benchmark. And the task is as follows. You're given as input an image, and it contains a Python script. You have to run the code, and then the output of that code is going to be URL. That URL is going to have a C++ code, and you have to compile it and return the sum of the 3rd and 5th integers. So it's quite mouthful. And this is a trace of execution from Magentic-One, and we'll see a bunch of demos, and I'll try to spin it up live for you. And the way this is going to happen is the orchestrator is going to govern this team of agents. So first, there's a file server agent that's going to access the image, extract the code. Then you're going to take that code from the image, analyze it, extract it. Then you're going to run the code in step 3 on the top right. That code is going to return a URL. You're going to ask a web navigation agent to web server to go to that URL, extract the code from it. Then you're going to go back to your coder agent, analyze the code, and then execute it and return the result. So that's the kind of tasks that require different capabilities. So web navigation, coding, executing code, handling these files of different modalities. And this is not a workflow that I predetermined. It's a workflow that was task dependent. And we're going to go through how the model and the system determine this workflow. And before that, I just want to talk a bit about the single agent versus multi-agent paradigm that's a bit emerging in the literature. And the advantage of this multi-agent architecture are twofold. So one is flexibility and modularity. Because you're differentiating the different capabilities into different agents, you can use different base models for each of these agents, different prompting techniques. And having this dynamic orchestration can allow you to easily add or remove agents based on what your task needs. And the other kind of even more important advantage is reusability. It allows you to define agents first, have those agents be reusable components, and then stitch them together in a team if you need to. So essentially kind of like a object-oriented programming paradigm, and your code becomes much simpler to maintain versus a single agent workflow where everything is linked together and you cannot test individual pieces separately. Any questions or thoughts so far?
Okay, cool. It'll work.
And there's, of course, lots of limitations that I'll touch on at the end. So let me first introduce, the power rangers behind Magentic-One, and then we'll go into how we stitch them together. So the first agent is this web server agent. So it's an LLM with tools that governs a Chromium-based browser. And essentially, given a natural language request, the web server is going to perform an action and report back the state of the web page after performing this action. And the specific implementation of this web server is as follows. So the action space is going to be either to click a button on the web page, scroll, input text, navigate to a URL, search. And its representation space is a screenshot of the web page with set of marks prompting. So set of marks prompting is basically putting these bounding box on every interactive element of the web page. And you can extract these interactive elements from the accessibility tree. And so you extract each of these interactive elements, you put a bounding box and a label. So you put, box 1, box 2. You feed this screenshot plus a version of the accessibility tree to the LLM, and you ask it to choose an action.
This is a small thing, but does everybody implement an accessibility tree on the web, or does very commonly fail?
So essentially, it just depends on the amount of information it contains. So you can always have the interactive elements. Now the question either you have a good description of them. So because the DOM is always available, but just depending on how much each element in the DOM is described using the accessibility tree, so you can have extra information about what a button does, its description, and so on.
These things can be all messed up depending on the website, right?
Yeah.
Different websites are different quality.
Exactly. Even if you don't have the accessibility tree, we have a new model called OmniParser, which does this parsing and tries to come up with a semantic description of each of these bounding boxes if that accessibility tree is not accessible, or you're operating in an environment that's not the web, like a GUI application that doesn't have that information readily available. So we have some other measures, if accessibility tree is not available.
So just a question about that. If the web server agent was having trouble because the accessibility tree wasn't good enough, it would report failure back, and the orchestrator would decide to call this other agent. Is that how it would work? Agents aren't talking to each other, right?
So that's so there's a model our group released. It's called this OmniParser model. It's not an agent. It's essentially a screen parsing model, and it just replaces this parsing. And so either you use that to parse or use the accessibility tree. We could have developed an agent that uses that parsing instead of this parsing, and you could do exactly the way you said. If this reports a failure, you could call that other agent. We're not implementing that, but that's kind of part of the work going forward. Does that make sense?
It does, but it sounds like so who calls? So the web server agent would call the OmniParser, right?
I'll talk about the orchestrator will do all those decisions.
Yeah, thanks.
Yeah. And even if the accessibility tree is not perfect, you still have the screenshot, and the screenshot has has enough information for a human. If the vision capabilities of the models are good enough, it's going to do this job without them. And even if you remove actually any of the information from the accessibility tree, it still works well enough, not as good. The other agent in the team is the file server. So this is an agent that controls a file preview application. It sees your current working directory and can navigate between directories, list directories, open file, export them to the chat. So if you have an image, it knows what to do. If you have a PDF, you can parse it, CSVs, then all of that stuff, it can parse them in a way that the other agents can interact with them more easily. The third agent is just a coder agent, we're calling it. It's basically just a raw LLM with no tools and just a very long system prompt, it always starts, "You're helpful." That's just, very well tailored to work in the system, via how it creates files, how it executes the code to interact with the other agents. And the final agent is this computer terminal, which is just a shell to execute code, install packages, and so on. So these are the worker bees of Magentic-One. And at the head of this team is what we call the orchestrator. And this is going to govern the operation of the entire system. So this is really where most of the work has gotten into. So let me walk through it step by step. So you're given a task. The first step is to create something we call a task ledger that's stored within the orchestrator. So this ledger is going to try to figure out if there are certain facts that it needs to look up or derive. It's going to try to attempt an educated guess at solving the task directly. If the task is simple and requires no steps, just the orchestrator can immediately guess it. And it's also going to try to come up with a step-by-step plan to tackle the problem. This is a process I'm going to refer to as the outer loop of the orchestrator. This manages what we call the task ledger, consisting of facts, educated guesses, and a plan. And these are essentially things stored inside the orchestrator and shared to the users as just a message. And so after you come up with this task ledger, now we enter something we call the inner loop. And so you do this task ledger at the first step. The second step is going to be computing this thing called the progress ledger. And the progress ledger is essentially a dictionary that's stored in memory. And at every step, the LLM is going to try to fill that dictionary, that ledger. So the first thing is going to ask itself, did I complete the task already? So that's a Boolean, yes or no. Am I in a loop? Again, that's a Boolean, yes or no. Am I making progress? Yes or no. Who is the next agent that should do something? And the answer is the ID of one of the 4 agents in the team, or any of them that you can add. What should I say to that next agent? So a string request to that next agent. So you compute this ledger at this step. The first thing you check is, did I complete the task? If that's a yes, you report the final answer. Or if you didn't compute anything so far, you just report your educated guess. If you did not complete the task, so if no, now we check, am I making progress? If I'm making progress, okay, let's continue. So if that's a yes, then what will happen is the orchestrator will delegate execution to one of the 4 agents we previously described. And it's going to send a message with the instruction that's stored in the progress ledger to that agent. That agent will perform one action and then return back their observation. Now, if you determine that you were not making progress, we keep a counter in the orchestrator that keeps track of how many times you have stalled. And stalled essentially is how many times you have not made progress so far. If that counter is below 2, then you just continue as usual. But if you've tracked for 2 consecutive steps or 3 consecutive steps that you have not made progress, what essentially we will do is we go back to the outer loop. So this is the flow, right? So I'm here, I've not made progress. If I've not been stalling, okay, I just go back and keep this inner loop of recomputing the progress ledger, figuring out the next instruction, calling the agents. Now, if I'm in a state where the stall counter is bigger than 2, I will exit this inner loop and go back to this outer loop. And now in this outer loop, what I will do is I'm going to reset all of the agents, because all of them, at this current state are stuck. And I'm going to instruct my orchestrator to come up with a new plan that tries to address the failures that it ran into. So essentially, it's going to try to rethink step by step, what went wrong and try to come up with a new plan or new educated guess. So this gives it a chance to just try again. And now it comes up with this, new plan that it stores as a message to all the agents, and then goes back to the inner loop step by step, computes the progress ledger, and then tries to do the work. Question?
I do want to let you keep going with the talk, but so first of all, I think it's really fascinating that how many of these cool systems involve a combination of workflows and just sort of planning, LLM planning techniques, and this is an interesting workflow. And in that context, it seems like it's a nice augmentation of a simpler React style thing.
Correct.
And whether it's calling other agents in a multi-agent framework, or whether those agents, we just want to call those tools, in which case it's more like a React system. It's kind of cool. But specifically here, is there some module which is looking at the failure and updating specific facts that are diagnosing what's gone wrong? I didn't see how's that's happening.
Great. So this ability of the system to replan or reset itself is what comes in when it's getting stuck. So if we see ourselves getting stuck, we have a different prompt that takes in the messages that were sent during the last trace of execution, and just basically ask the model to reflect, like, this is your previous trace, you failed. This was your previous plan. Try to come up with a new plan that tries to mitigate those failures. And then it tries to redirect those things. So it's just an updated prompt for the task ledger to just reflect on the previous execution trace. And then essentially all those agents starts from anew. Now they don't have access to the previous context on purpose, because you don't want them to repeat the same mistakes over and over again.
Thanks.
So when you say, when you say you go back to the outer loop when you get stalled and all the agents are resetted, does that mean all the agents have individual states within the same inner loop, or do they share state with the ledger, or how does that work?
Yeah, so there's a couple of things that are stateful. So obviously, the chat history of each agent, you can reset that. So that's stateful, and that's maintained across these agents. They share the same chat history. The other thing that's stateful is, for instance, the web surfer, because the web surfer is pointing to a specific web page, and you want it to go back to your home page just to get stuff of that state. So that's something you reset. And then similarly, you can reset the computer terminal if you've installed wrong packages or delete certain files you've created. Thanks. Yes.
How do you define the scope of the sub-agents that they are doing the task? For example, like for web server, if I ask some philosophical question, what is the meaning of life? You can imagine that web server could go on forever, right?
Great question. So the orchestrator is given a description of each of the individual agents and a sentence or two about their capabilities. So it knows, if I need to do something web-based, I should not ask the coder or the file server. I should only ask the web server. So that helps. And then if you give it an instruction that's to the web server that doesn't require it to do something, it will just return a string answer. Mm-hmm. And so it might just, give you the answer of life, but then nothing bad is going to happen, essentially. Does that answer your question, or?
Yeah, a little bit. One of the questions that leads me to this question was what about if the agent is taking execution for a long time? How does an agent know when it's stuck, or inform the handler agent?
Okay, that's a good question. So here, each agent can only perform one action, which is essentially one LLM call.
So one concrete action.
One concrete action, and then you go back. That's obviously going to be super slow and costly, but that also ensures you're going to do better on the task, because you're just using more calls, more reflection at each step, but it's going to make things way slower. So there's just a trade-off there. Question there?
This system and many others like it,
Yeah.
we sort of treat software with LLMs as if we have a kind of access to a little person. So the design decisions we make, like for example, the questions that you ask in the ledger, or how the loop works, is us thinking, how does a person do it? Maybe we'll just kind of make it really explicit. But often I find that I can't tell which of those decisions mean anything or whether they are helpful or not. So for example, if you remove the educated guesses line and added make 5 task plans and choose the best one, does the system change or is it the same? And this, I have the same question for basically every part of the system. Was like, which things matter? As the research goes forward, the evaluation has massive variances because small changes and randomness can cause a catastrophic failure one time and a complete success another time. So what do you personally feel matters in the system as a real kind of change that's deep?
Good question. Good question. We have one ablation where we get rid of all of this logic and replace it by just a loop that decides which agent should speak next. Nothing else. So it's just a dynamic orchestration, but then none of this stalling logic or none of that. So what I will tell you is important. I think a lot of the stuff in the task ledger is important to like quickly, if you figure out the task quickly, you can just quickly execute the loop, right? Because you figured it out. But even if you don't figure it out, one of the agents will do it. And then you're just like costing 2 more API calls. But in terms of metrics, nothing's going to change because they could just rederive it themselves. Now, the 2 things that I think are really important is this stalling logic, this ability to replan. If you remove that ability, like maybe 20% of the tasks start failing. And this happens a lot in terms of replanning, just because of the variance of the LLM. You know, essentially here, you're running this workflow maybe 2-3 times per task because it's stalling. And so it just helps. Because you could put it in a loop and run this 3 times,
Yeah,
right?
that's what I was going to ask.
But then this just does it a bit more smartly than that.
Okay, but it's not that different from just running it 3 times.
It's not that different. And if you run it, like you could run 10 times, we have those experiments, not maybe in this paper, but you can just boost those numbers.
Okay.
But then you're just, I guess the thing that's missing from the current evaluation scope is cost of the model and then accuracy, right? And those things trade off. And then just like this self-reflection about, essentially, the stall count and like all of those ledger questions to determine that stall count, I think are important. The other stuff, maybe not so, but it's just doesn't hurt at least.
Thank you.
Make sense?
Yeah, thank you.
Yeah, I guess to Sergio's question, could you say something a little bit about your development philosophy? Like you said, you have one ablation in the paper, but you have some intuition about what helps or doesn't help. How are you developing that intuition? Are you just measuring on one data set and then improving this over time, and then eventually you evaluate on all the held out tasks, or how are you as a team going about improving the architecture?
Yeah, so almost all of the benchmarks we have evaluated on, we had never touched them before running on them. And they were almost at the end of our development. But I think the initial development started with the development set of Gaia. That was kind of the space where we tried to run things again and again. Gaia has also a test set, which we're reporting numbers on that. But essentially, that set of Gaia was our testing ground to develop these different things. And yeah, it's essentially nothing we didn't have any fancy hyperparameter techniques or lots of different ablations. It was just looking at traces, interacting with the model as much as we can, and just figuring out what made it work on the dev set. So does that answer fully your question, or were you looking for something?
I mean, it's a complex system. I mean, it would be nice if one could kind of search over
Exactly,
space more automatically.
But then everything is so expensive here, so you just have to do things smartly. Yes.
Yeah, I'm just curious. I mean, maybe related to the question of what works, what doesn't. Have you, looked at a lot of these, ledgers and these progress being made decisions to see, how often does it actually get this stuff right, and how often is it just kind of randomly sort of stumbling into the right answer?
That's a good question. So we have a work on like debugging these systems that's led by one of our interns. And just, we don't have rigorous measures, but just qualitatively, what I feel interacting with it and like watching it do lots of things is, for the most part, they do make sense. They are a bit more conservative than not. So a lot of times it will say, I'm in a loop, while actually it's doing the right thing. And so it's mostly on the conservative side rather than not conservative side. So it is often resetting and replanning when maybe it shouldn't have. So that's the only remark like I can make that I'm kind of more confident about.
Like that's it. And I'm, you think about like when it chooses fact to look up or derive, do those make sense?
Those do make sense most of the time, I feel like, but then they don't actually like contribute a lot to the system. They're just kind of helpful things. You can just think of it as like just chain of thought, essentially. Like it's nothing much different than that here. But I do think the ledger paradigm is kind of a nice way to work with these systems. You can add more questions to it, like things you want to keep track of. Maybe you want to keep track of like specific things you've encountered. And so I just found it like a nice way to do prompting with this ledger. So you just ask the model to return a JSON at each step, and like you do everything based on that JSON.
Is this a real usable system? Do you use this over ChatGPT? Like, what is this experience based on?
So it's very good for certain things. If you have a task that requires going through like specific pages in the web that like a web search would not find, then this is actually would be better than ChatGPT. But for almost all other things, ChatGPT is going to be much quicker to answer your queries. And so those like bit more elaborate tasks with lots of steps and require deep search or repeated like execution, coding, like returning the answer with the web search are like the things that's like really excelling at. Now, it's not what we're touting as a user-facing solution. This is not a user-facing solution. This is like our attempt at the best autonomous system. We have another workflow on like how could we make this usable to a person, and that's going to be very different design decisions.
How would the design decisions be different?
This is, I mean, you could make this more user-facing, for instance, by adding, and this is very relatively easy to show. I'll show a demo of this. You could add a user as an agent. And so if you gave it a task that's not well specified, it could go back to you, ask you for clarification, then go back to doing its thing. If it's stuck, like it doesn't find the right link, it could just ask you for the right link and then go back to doing its thing. So that just helps it a bit more user-facing. And then the other like more just simple thing, the logs of these agents are just not readable to a person. It's just spitting out a lot of things, like a lot of this chain of thought type reasoning, like you don't want to ingest as a user, and like it's very hard to understand. So there would be a lot of work in formatting the messages so that they're easily absorbed by a user.
So in our architecture, one thing that we've played with is having something called an interaction manager, which sort of corresponds to the agent that would communicate things to the user. And I think the key challenge is that it really needs access to the detailed state of what the individual task agents are doing. And so it's hard to decompose the presentation communication layer from the actual task agent layer. So that abstraction hasn't worked as well.
Got it.
For us yet.
But I guess like the way you might want to think of it is like you produce two types of messages. One is meant for agent consumption and one is meant for the human consumption. And like, yeah, for the agents to work better, you keep those internal messages, like almost internal reasoning steps hidden, and you just show the outer thing. And that's might be what you want to do here. Any other questions? This is kind of the meat of the work, so it's fine for us to stop at this.
I have one.
Yeah.
I've been working on a practical system at another job that I have, and there we found that LLMs make a lot of consistent mistakes that are sort of kind of stupid, quote unquote. And we have to intervene with regular code, not LLM decisions, but just kind of say like, okay, the LLM is going to do the following kind of things. We're going to check for them and fix them. So just have pieces of code that we insert all over the system to fix common mistakes that
Okay.
are not really, it's not like, oh, it's GPT-4, oh, it's not smart enough. It's more like, oh, it just makes this one dumb error all the time.
Okay.
So we know about that. Did you need to do this here, or because it's more of a research, you didn't actually sort of try to fix the bugs that are fixable with code as opposed to waiting for GPT-5.7 or whatever it is?
Yeah, we didn't try to do that. Like there are some interesting things that happen. For instance, like the web surfer is navigating like a real Chromium browser and sometimes goes into errors. And so sometimes the orchestrator decides, let the coder write like a raw code to like go into a web page and like do the thing that the web server should have done, but it could not do.
Does not work very well.
It sometimes like the web server actually works pretty well, but sometimes like because of a CAPTCHA, it's like you stall, and then the orchestrator decides, okay, let the coder try to like write Selenium and like fix it. And so you have these weird behaviors that happen.
Usually you could use this yourself. I mean, doesn't AutoGen have like this user proxy agent or
Yeah, yeah. I'll show me. I'll spin it up for you. I have it running in the background. Yeah, maybe just like just to show you the execution traces.
Where is the best form of sandwich? I assume you're talking about the side.
What's that? Tandoor maybe not the best. There's like shawarma time is not bad. There's a few places on like your district that are. There's one Lebanese place has like good shish kebab sandwiches.
LLM doesn't know such thing.
The LM is not good taste. And so essentially this is the task ledger I was talking about. So, you know, this is, we're working to address this request. There's a description of all the agents. So it's not very good for web surfer, coder, essentially, these are the facts. The things to look up, the menu, the ordering options, the educated guess, and the plan. And this is essentially the ledger we were talking about that's completed at each step, and you're going to see it. So is the request satisfied? The request is not satisfied because like we haven't done anything. We haven't done any action, so we're not in a loop. We are making progress. The next speaker should be with the web surfer, and this is its instruction. Now you'll see the web surfer spin up. It's going to search for Tandoor. It goes into an error, so it's just going to search again. So it goes on Bing, search for it. We're still making progress. So it's going to click on the Tandoor website, you know, navigate to the menu. It's going to go to the shawarma, like.
And this is using GPT-4o?
This is using GPT-4o, correct. So it's going to do a lot of these things. Here's another one. Kind of relevant to here, where I'm just showing the file surfer and the coder agent. So I just gave it like a PDF. I don't give it the PDF. I just tell it like there's a PDF in my working directory. Like go find it. Again, it's like gonna come up with a plan, and then essentially the file surfer is gonna read this PDF and like export it to the other agents in a message, so they could absorb it. And it's just gonna keep scrolling through the PDF to extract the references, because like, and then it keeps extracting them, and then essentially, once it extracted the references from the paper, it's gonna ask the web surfer, okay, search now for papers. Could have used semantic scholar, I think just the Bing search. It's gonna keep going through, find the papers on archive, and it just finds one that the paper did not cite. And like it exports its bib to a file essentially. And that's kind of what it's gonna do here. So this is just a walkthrough. Now for evaluating these systems are really tricky. So one thing is like, you want to evaluate different agents on equal ground. If you have an environment where like all your Python packages that you can dream of are already installed versus one where nothing is installed, it's a big difference, because like the agent with no packages has to install them. Like it has to create that code, run it, and figure out what's installed. So it's a small thing, but makes a huge difference. That just to speak about like the minor details. And then there are dependencies between tasks. If you're running things on the same computer, like you've previously downloaded the file, now you don't have to download it. Your browser history might contain like the previous traces. The libraries might be already installed. And you don't want to log things inside the same system, because like the system can access those logs and modify them. So we developed like a lightweight solution to help with this. It's called AutoGen Bench, also on the AutoGen repo, where like every task is run on a fresh Docker. You could parallelize things and like do centralized logging just to have things a bit more concrete. And we evaluate on 3 benchmarks. So those are Gaia, Web Arena, and Assistant Bench, and they're all like web-based.
Stop, can you go back,
Yeah.
just talk a little bit about the safeguards?
Yeah, oh, sorry, I didn't mention that. So one thing is like for code execution, you actually run that in a separate Docker as well to not modify the system. We do have like a small safe list of URLs like that the agents should not go on to. What other things? And I think we're just like, another safeguard is like, you have to have someone like inspect the logs. Like every few runs, like someone stopping them, looking at the logs, seeing what's happening. Because like, I'll talk a bit about like some of the wonky stuff the agents did, like while doing the benchmarks at the end.
Cool.
Yeah, so those are the 3 benchmarks. And just to give an example, I've already shown like a multiple Gaia examples, like the country one, the coding one. But the assistant bench is similar. Like the question is like, which supermarkets within 2 blocks of Lincoln Park in Chicago have ready-to-eat salad under $15? So it's not a trivial question. Web Arena, if you're not familiar with it, it's a synthetic web environment. So they created like their own websites from scratch, and you have to spin it up every time you run a task. And there's like a fake Reddit, a fake GitLab, like a fake shopping site, a fake Amazon, and you can run stuff on them, like buy things, post comments, and one task is like, tell me the count of comments that have received more downvotes than upvotes for the user who made the latest post on Shower Thoughts forum. So you have to do lots of steps through the environment to solve this. Just implementation details. Everything is built on AutoGen 4.4. It's in pre-release right now, but all of our code is open source, and all of these models are GPT-4o, and we have some ablations with O1 as the orchestrator. And so let me walk through the evaluation. So the y-axis here is accuracy, basically a 0-1 measure of task completion. So this great thing is GPT-4 with no tools, with nothing, just trying to answer the question. So it's clearly much worse than everything, but it does solve like some basic questions that it just has them in its memory. I want to highlight like the 2 baselines we're comparing to. So the tricky thing, there's no agent system who had evaluated on any 2 of these benchmarks. So each of the baselines we're comparing to is like benchmark specific. So a different system for Gaia, different system for Assistant Bench, different system for Web Arena. Because none of the other solutions were trying at least to evaluate on Gaia and Web Arena, or Assistant Bench and Web Arena. It's the combination of them.
Yeah, doesn't like browser gym have multiple of these in it?
So all of the browser gym environments, except for like Mind2Web Live and Web Arena, are synthetic. So it's like MiniWab, which is like just a very simple.
But they have,
Text-based.
they have assistant bench.
Oh, I think it's just like half a month ago or something. It's
Oh.
like after we.
Gotcha.
So it's just very recent. Is it? I think the main thing I want to point out is like Gaia. I think it's like many years ago, and Web Arena have been around for a while. This is then just like pretty recent. So for assistant bench, we're mainly competing with like the creators of it and one or two groups who try to upload results. So yeah, and I'm trying to make a difference between benchmarks, baselines that are open source versus non-open source, because that makes a bit of a difference because you have no idea like what they're doing under the hood. So Gaia and Web and Assistant Bench have a hidden test set answers, so it's a bit harder to gain those benchmarks. Web Arena, the test results are out there, and so many people train on the def set of it and like report on the test set. And so for Gaia and Assistant Bench, we're very comparable with the current state of the art. Slightly edging on Assistant Bench, but very equivalent on Gaia. Now for Web Arena, so that's the purple. One is, and I'll show the difference between 01 and 4.0. So that's the Magentic colored plots, and the green is the baseline. So very indistinguishable, but on Web Arena, you just see a big jump from one of the non-open source state-of-the-art systems. We don't have much clarity on what it's doing that making it so good, but that's kind of all I've had to say. And the third thing is just the huge gap still into human performance. So Gaia humans are 90%. Web Arena, I think this is very conservative to be at 70%. So there's just a huge gap to human performance on these benchmarks still. Digging a bit deeper into subset level evaluation. So this is for Gaia and Assistant Bench. Categories of the benchmark. So level 1 is easy for Gaia, level 2 is medium, and level 3 is kind of hard. And this is our system with just 4.0, and our system with 4.0 and 01. 01 playing the role of the orchestrator. And just trying to see like where is 01 giving us a big gap in terms of improvements. And I think the biggest gap, at least we've observed, is just it does the easy things better. And we're not seeing a big improvements in some of the harder tasks. But it is making the system better, but not to the extent we'd imagined. And maybe it's just because our system is not very built for an 01 type model to interact with it. So maybe it is suboptimal for that, but just plugging 01 is not giving us the boost that's been reported in other benchmarks.
Understand it's like really hard to understand the failure modes because everything is each example is complicated.
Yeah.
But did you try 01 instead of where the 01 was driving the task agency?
Yeah, so that's a bit harder because 01 is not multimodal, and then 01 doesn't support tool calling, so it's a bit hard to plug it into the other agents that require those abilities. So, and 01 is like, and 01 has a higher rate of refusals by far than GPT-4o. And so when you were asking it to like play the role of the web server, it would just refuse. Why? What? I don't know. We like documented a lot of it and a bit of it in the paper, but just say like, because you would try to get it to go to Reddit. Like, we don't report Web Arena because 01 even refuses to do anything on that benchmark because it requires posting to Reddit.
Smarter and smarter.
I said just refusing to do that. That's like very human.
Reddit is a bad idea. You shouldn't go to Reddit. So it's right.
You don't have access to it without the refusal. Maybe you didn't want to report it.
No. And here is kind of the ablation I hinted at. So this is the full system. This is on Gaia. And I'm just reporting on the y-axis number of successful tasks. This is the same system but with a simple orchestrator that just decides who speaks next with none of that stalling. So you're seeing like 20 tasks now starting to fail, and this is kind of repeated. If you remove the web surfer, you're also having this big gap. If you remove only the file surfer, you're also witnessing this big gap, and that's very understandable because some of the Gaia tasks require you to open a file. And if you don't have that capability, you're just going to fail. You don't see such a big gap when removing the coder. And the reason is the orchestrator could play the role of the coder because they're the same model, and it could just spit out the code instead of asking a coder. And if you remove that subset of agents, then not as
And
much.
this is using what?
4.0, all 4.0.
All four.
Yes.
Right. So it'd be really interesting to see variations on the simple orchestrator where.
Yes. So we could do more ablations just for the orchestrator to understand what worked. Any questions on the evaluation?
How much does it cost and how long does it take to run one ablation? Let's say your code is open. If I want to do the ablation myself, what kind of cost would you expect?
With the newest 4.0, with like prefix caching, it's becoming cheaper, maybe like $50 per task. But yeah, you expect to spend like $100. So it's not cheap. And that's kind of a huge gap of this work that we're trying to address.
I guess, and like Dan was saying, I think it's hard to tell. Is it certainly automatically? Do you know, like, when the system fails? Is it because the orchestrator does the wrong thing, or is it because the web surfer can't actually access the right information from the page? Or yes, like which of these systems is to blame for?
Yeah, we tried some analysis in this paper, and we have some work that's trying to like do much more error analysis. There are some themes we've observed, like some of the agents not adhering to the instructions. It's a common failure. A lot of the failures happen in some of the coding parts of the agents. So the communication between the coder and the terminal, like for installing missing libraries, for finding certain files that they should, create or not create. And there's also a ton of like web surfing errors just because of the, like, you might want to click on something and it exists, but sometimes it just fails. Or sometimes on one run you encounter captchas, on another run you don't. And so there's just variability from that. So there is a lot of sources of random errors and like big error bars on each evaluation. Just from completely, even if you set temperature to 0, you're still going to have errors just because of the environment you're interacting with. Yeah, and then, you could plug in a human into Magentic-One and have it do stuff. Me ambitiously try to run it and see if it's gonna work here. Let me just share my screen. Sorry. All right. So I'm just gonna tell it, I have a meeting with Dan Weld. Please help me prepare.
The heck should I tell him?
Let me actually share my entire screen so you could see the browser also.
I'm glad you asked. Dan Weld is known for his dry humor. He enjoys wearing various clothes.
Okay, so the user has a meeting with Dan Weld. Information about Dan Weld. And so the plan is like, look up Dan Weld's position, discuss with user proxy what's the meeting, prepare discussion points. And so we've already like done a few things. And I think, okay, Dan Weld, we're looking up Dan Weld online. So let's see what it gave me. Here's some basic information. Okay. Consider discussing. Okay. Didn't help me that much. So let's try to run it again. Maybe I shouldn't have done this, but it's informative. Let's run it again. Spin up the browser. And
So you have to type ask me for anything you need.
you don't have to, but I just wanted to show it like coming back to me.
I see.
So
I
trying
mean,
to-
like if you don't do that, would it come back?
it would. It would.
Although it's not very good in my experience, it doesn't know what a clarifying question is for when
True.
it's important because it doesn't have a mind. So the notion of clarification is ambiguous.
Unless it's trained, like I think
Yeah.
through just the RHF, yeah.
I thought I saw it flash by very quickly in the first trace. There was like ask the user what the meeting is going to be about.
And then-
I didn't quite make it to the output.
Correct. So the plan is like a hint in the prompt. It's not a strict plan that's you're adhering to.
Have you tried to make it adhere to it?
Yeah, and so there is also like bimodal, where if you give it a really good plan, it's gonna do amazing things. But then if the plan is not great, then it's not gonna do very useful things. And so it's kind of like if you have a preconceived notion of what a good plan is, then you should just like give it to it. And you can modify the orchestrator to work with like a structured plan. And that's going to be in a future work.
Mhm.
It looks like you're already trying to influence the ledger in your query. Like,
Yeah, essentially, yes. There's also so much variability. Like the model we tested on, it's like 4.0 of May, like at the Azure endpoint versus the OpenAI of August, things change. And so there's just a lot of variability because we don't control the models. That just happens, and things don't stay consistent over time. Which is why I moved to like more open source models is also something on the agenda for us. So yeah, big limitations, cost and latency, especially if you're working up with O1. You're talking about a few dollars, 10 minutes for the Gaia tasks that require like these 20 steps. The coding abilities of this agent system are very underpowered compared to some of the state-of-the-art systems we're seeing for coding. And it has no capability to like learn or memorize past information, which could really help it in some of these tasks. Now to kind of the final point is about risks and mitigation. You have these agents like unleashed in this digital world, and like there's so many risks that can happen. And so at the minimum, you have to have them understand what's reversible or not and constrain their action space. And so examples of risky behavior that actually happen during these benchmark runs are, posting to Reddit and social media, emailing textbook authors like for stuff because their textbook is not available online like easily, and like it even drafted and like was about to send a freedom of information request to like the government, and like many times it would go on Amazon and like send a help request because we didn't log in, so it couldn't buy anything. And so just so many weird things that would happen if you let them loose.
I look forward to our AI future.
AI future. So yeah, our code is online. You can read the paper online also, and we have blog posts with some of those videos as well. Thank you so much.
After this, are you more optimistic about AI future or more pessimistic about AI future, or a complicated mix of the two?
I am optimistic. Like, I think there's a future where this interaction is very fun. Like, it's very fun to watch the system do things on your computer. I enjoy it. I don't know, others might not. And if it's gonna help me do repetitive things or not, that's gonna be fun. But I think there's a lot of work we have to do to prepare the web for agents to live in. Like, you could imagine starting, we have a robot TXT, maybe we'll have an agent TXT for like future websites.
Or like an LLM API for a website?
Exactly. And then thinking more about the future, and I think we talked about this a bit, is in the future, like right now, these agents run into CAPTCHAs all the time. But maybe if your agent is an authorized representative of you as a person, maybe you pay a fee or something. You don't have to run into CAPTCHAs. But the risk is like anything bad that it does, you are liable. And so you can separate between like authorized agents versus like rogue agents. And then
Why do I still have to answer captchas?
Because you're a suspicious character. I answer a lot of captchas on Firefox because Firefox is a suspicious browser.
yeah. But these agents just run into way more CAPTCHAs than you would run into because like it's just gonna detect. And so you can imagine like just like having some agreements with these sites, or to just have like, okay, this is my Magentic-One agent. It's my representative. Okay, go do your thing. So it's gonna be a fun feature, maybe.
Thanks.
Just